All right, let's go ahead and take a look at the next problem that we have. Um, this one is asking us to solve for the Thevenin-Norton circuit. You'll notice this one's a little bit different uh, because, dun dun dun, we have a dependent source. Uh, this is new to us. We haven't worked with these before, but fret not. The process is going to be slightly different, but it's easy enough to work with. Okay, so in general, we're still going to imagine that we have that imaginary wire out to the side here. But what we're going to do now is that we see the dependent source. It has to come with some sort of equation that's associated with it. So what does that source depend on? And if we take a look, this one depends on Ix, and if we go look for I of x, it's right there. So if I of x was to increase, then this source would also increase. If I of x was to decrease, this would decrease. So it's a proportional relationship there. Okay, but let's take a look at what we have. What we're going to end up doing is, in order to solve for these values for VThev and RThev, we're going to do it in a different order. Now we're going to have to solve for VThevenin first. Okay, so we'll have to do VThevenin. So to find VThevenin, we see that looking at this circuit that we have, no current is going to travel down either one of these open terminals. Okay, so let's just kind of imagine it's like that. Well, that's two blocks set up, and if we were to go drop a handy dandy ground there, then we can do a nodal analysis on it, everyone's favorite technique. So if we do the nodal analysis, where we have at V1, like this, like that, and then we're going to assume it's going that way. So if we do that, this is the V1 nodal analysis. So this will be I of x, this will be 0.5 I of x, and we'll call this one like I of 2. That'll be fine. So if we go and write this out on the side here, so I of x plus 0.5 I of x plus I of 2 is equal to 0. All right. So now if we can come here and see what we have, we see that if we go look at the I of x down here, so this will be 0, 0, 0, 0. We'll pick up 15 volts, and we'll have 15 volts at. Okay. So we see that the I of x, but if we write it out, I of x, reality is going that way, so that would be 15 minus whatever V of 1 is over 5. So if we expand this out, I of x from this equation is going to be from that equation. It will be V of 1 minus 15, because remember, we're going from here to there for this equation, over 5. We're going to do plus 0.5. We'll do I of x here. Then I of 2 is going to be V1 minus V of g over total resistance, which is 20, and this will equal 0. And if we go ahead and multiply the entire thing by 20, we'll get 4 V of 1 minus 15 plus 10 I of x plus v of 1 is equal to 0. But here we need to go and plug in the I of x, so 15 minus v of 1 over 5 plus v of 1 is equal to 0 for v of 1 minus 60. So this will just cancel out to give us 2, so this would be 4 v of 1 minus 60 plus 30 minus 2vi plus v of I is equal to 0. 3v1. 3v1 is equal to 30 volts, so therefore v of 1 is going to be equal to 10 volts. Okay, so that's the first part. But the good thing is that we can find the voltage drop across this 10 ohm resistor, and because these two branches are going to be in parallel, there and there, then if we can find the voltage drop across the 10 ohm resistor, we find the voltage drop across the open circuit. So let's go do a voltage division, where we have v of 1, this will be v of 2, this will be 10, this will also be 10, and defined here to there. So v of 10 is going to be equal to 10 over total resistance 20 times voltage V1. So that looks like that'll be 100 over 20 times nothing, which will give us 5 volts for V Thevenin because it's in parallel. All right, so there's V Thev. Okay, so now that we have done that, it gets a little difficult, a little bit off the beaten path from the typical Thevenin problems that we're used to. It's going to look like something where we now include those two wires and complete the short circuit. Okay, so we had to do a new KCL, and this time we'll do it with the short circuited wire. So now, because of that, V of 2 is going to be equal to 0, because down here, that's 0, that's 0, and then now we have this closed wire, so 0, 0, 0, 0, 0. So and V of 2 will also have to be equal to 0 because it's on that same point and there's nothing in between them. So by that flow logic, it'll actually make it a little bit. So we can come in here and do the same KCL back at V1 because now the currents are going to be a little bit different. So we'll still have I of x times 0.5, and then this will be I of 2. So I of x plus I2 plus 0.5 I of x equal to 0. And it's effectively the same problem. So v of 1 minus 15 over 5 plus v of 1 minus now v of 2 over 10, because we're crossing over 10 ohm resistance. And then we'll do plus 0.5 I of x is equal to 0. And then now what we'll do is we'll solve for v of 1. So we'll come in here, do a similar process, multiply everything by 10. So this will be 2 v of 1 minus 15 plus v of 1 plus 5 I of x is equal to 0. But then now we do this. where we say 5. We'll plug in 15 minus v of 1 over 5 is equal to 0. And then these 5s will cancel, so we'll get 2v1 minus 30 plus v1 plus 15 minus v of 1 is equal to 0. So therefore, we will get, those two will cancel, so we'll get 2 v of 1 is equal to 15. So v of 1 is equal to 7.5 volts. So this is the new voltage value for right there. So if we're looking at this problem now and we see that current goes that way, well, if it has an option of going down this way or going down that way, it's going to see that the way to the right has no resistance on it and the way down has resistance. So it's going to bypass going down and completely send all of its current to the right. So the current I2 that we see there is going to be the short circuit current. So I2 is equal to I short circuit. So I of 2 is equal to V of 1 minus V of 2 over 10. So it will be 7.5 minus 0 volts over 10 ohms. And this, therefore, that'll give us I short circuit, which is equal to I Norton, to equal to 0.75 amps. Bam, 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 bam. All right, so these problems are a little bit different, but they're not the most complicated thing. Just a little bit of practice, and you should get these down just fine.